Hey, welcome back everybody. We had been looking at some arithmetic operations, and in this video we're going to look at some logic operations, and in particular we're going to look at how we can apply bit masking using those logic operations. Alright, so the MSP430, it supports the mnemonics INV for inverse, OR for OR, and for and XOR for exclusive OR. No big surprise there. These operations are bitwise, meaning that they operate on each individual bit of a word or byte. So we can use either one, .b or .w, and it's independent of all other bits. So if I have 8 bits, like 0, 1, 0, 1, 0, 1, 0, 1, and I take the inverse of that, then I'll get 1, 0, 1, 0, 1, 0, 1, 0. It looks at only a bit at a time out of that string. And related to these mnemonics, or these instructions, are also bit select, which is BIS, bit clear, which is BIC, bit test, which oddly enough is just bit, BIT. The T is actually test in that situation. Compare, CMP, and test, TST. All right, so let's start with the AND. The instruction here is written and then the operand is source, comma, destination. And so it takes the source bits and it ANDs it with the destination bits, and then it stores that in the destination. So the destination is altered here. And again, it's a bitwise AND. It looks at the first bit of the source and it ANDs it with the first bit of the destination. Then it looks at the second bit of the source and ANDs it with the second bit of the destination, and so on. Now let's recall some properties of the AND operation. That first one there is x and 0 equals 0. Let's try to understand that. So if x were 0, 0 and 0 of course gives me 0. And then if x were 1, 1 and 0 gives me 0. So it doesn't matter what x is, x and 0 gives me 0. Now let's try to understand that second bullet point there, x and 1 equals x. Let's suppose x were 0. 0 and 1 gives me 0. 1 and 1 gives me 1. So in this situation, it gave me back whatever x was. So x and 1 is equal to x. So therefore, we can take advantage of this. ANDing with 0 will clear a bit or bits, make them 0. And ANDing with 1 preserves them. It keeps them the same. If they were 0, they will stay 0. If they were 1, they will stay 1. Let's look at an example. Let's say we had data coming in, 8 bits, 1, 1, 1, 1, 0, 0, 0, 0. We'll call that's representing x. That's the data coming in. All right, and let's say we want to clear maybe the most significant 2 bits, the 2 most significant bits, I should say. So what we're going to do then is AND the incoming bits with this string of bits 0, 0, 1, 1, 1, 1, 1. In that case, the most significant bits, the 2 most significant bits, will be cleared, right? Because starting at the most significant column, 1 and 0 will give me 0. And then the next most significant column, 1 and 0 will give me 0. But then all the other bits, because we're ANDing with 1, just retain their data. That is, they're preserved. So we get back 0, 0, 1, 1, 0, 0, 0, 0. Again, the 2 most significant bits have been cleared, and the other data in x have been preserved. That's pretty cool, right? And in this situation, the ones, you see, the ones that preserve the data are masking the data from being cleared, right? And so in this situation, though, we would call the entire 8-bit string that I have circled the mask. That is 00111111 is referred to as the mask. So we used a mask here to clear some bits and preserve other bits. Now, ANDing with 1 can test bits. Let's look at an example. Let's suppose I had an 8-bit data x given by 0001, 0000 as shown here. And let's say I wanted to test the most significant bit. In this case, I will AND it with 1, 0, 0, 0, 0, 0, 0, 0. The 1 is because I'm supposing that I want to test the most significant bit. Now, in this situation, the most significant bit of the data is a 0, so I'll get back 0 in the most significant column. And I'll get back zeros everywhere else because I was ANDing it with zeros there. Now notice, because the original bit, the most significant bit in the data, was 0, then I get all zeros back. That is, the 0 flag, because this is an arithmetic logic unit operation, gives me z equals 1. So we know that the MSB, or the bit that I was testing, was a 0. Just maybe you want to pause that, let it all sink in, but we'll look at another example. Before that, I just want to point out that this is the mask now in this situation. Okay, here's another test example. Let's say we have that same 8-bit data x, 0001, 0000, and we want to test the, what is that, the 0th, 1st, 2nd, 3rd bit, 0, 1, 2, 3, 4. Bit 4, we're going to test bit 4. Okay, 0 is the least significant bit, then 1, 2, 3, 4. So we're going to set up our mask with a 1 at the position that we're testing for, zeros otherwise. In this situation, we get a 1 at that location that we're testing for, and of course zeros everywhere else. So the 0 flag is 0, meaning it's not 0. So then we know that bit 4 in the data was a 1. Neat, right? And again, I want to point out that this is the mask in this situation. So AND can be used to clear bits and to test bits, or can similarly be used to set bits and to test bits, although we'll just talk about AND testing bits. So let's look at how OR can set bits now. This is as opposed to clearing them with AND. Let's look at some properties first, or I guess before that, let's look at the mnemonic and the operand. So OR's mnemonic is OR, and its operand is source destination. And what it does is it takes the source bitwise and ORs it with destination, and then stores the result into the destination, so the destination gets overridden. So here are some properties of the OR operation. X OR 0 is equal to X. Let's try to understand that. Suppose that X were 0. 0 OR 0 gives me 0. If X were 1, 1 OR 0 gives me 1. In both of those situations, I got back X. Let's look at the second property there. X OR 1 is a 1. If X were 0, 0 OR 1 gives me a 1. And if X were 1, 1 OR 1 gives me a 1. So in this case, it doesn't matter what X is. If I'm ORing it with 1, I get a 1. So again, now because of those two properties, we can use that to set bits. When we OR with a 1, that will set the bit, and if we OR with a 0, that retains or preserves the bit. So in this example, let's say I have data coming in, X, 1100, 0001, and let's say I want to set the least significant nibble, or the least significant 4 bits. So I will apply a mask, 0000, 1111. Now because of those properties of the OR operation, then the most significant nibble is going to be preserved, 1100, and then the least significant nibble has been set, 1111. Nice. Okay, now let's look at the exclusive OR. Its mnemonic is XOR, and its operand is source comma dest. And this takes bitwise the bits in source and exclusive ORs them with the bits in destination and stores that into destination, so destination gets overridden. Let's look at properties of exclusive OR operation. First one there, x exclusive OR 0 is equal to x. Let's understand that. If x were 0, 0 exclusive OR 0 is 0. If x were 1, 1 exclusive OR 0 is 1. So in either case, we got back x. Great. The second property there, x exclusive OR 1, is actually not x. Let's consider when x is 0. 0 exclusive OR 1 is 1. And when x is 1, 1 exclusive OR 1 is 0. So in either case there, we got back the complement of x, or not x. Therefore, exclusive ORing can toggle the bits, i.e. invert them, and we do that by exclusive ORing with 1, and when we exclusive OR with 0, we preserve them, so we can use this again to set up a mask. Here's an example. Let's say we have some data coming in, 0, 1, 0, 1, 0, 1, 0, 1, for the sake of the example. And if we exclusive OR it with 1, 1, 1, 1, and then 0, 0, 0, 0, what we're saying is that we want to toggle each bit in the most significant nibble. That's our mask again. And so we get a result then from those properties of exclusive OR, 1, 0, 1, 0. Notice the most significant nibble has been complemented or toggled. And then 0, 1, 0, 1, the least significant nibble has been preserved. Nice. So you might have a question then. If exclusive ORing is toggling the bits, like inverting them, why can't we just use the invert instruction? Pause the video if you want to think about it. But the answer is that exclusive ORing with 0 preserves the bits, which allows us to build a mask. The invert instruction will invert every bit in the data x and does not allow for such a mask, right? It just inverts all of the bits regardless. Okay, at the beginning of this video, we mentioned some other instructions. There was the bit set, BIS, bit clear, which was BIC. So BIS, bit set, it has a source and a destination, and then the result is stored in destination, and same with bit clear. Bit set will set, meaning it makes it a 1, bits in the destination corresponding to 1s in the source. Bits in destination corresponding to 0s in the source will be left alone. So this is like applying a mask, right? Similarly, bit clear will clear bits in the destination corresponding to 1s in the source. Bits in the destination corresponding to 0s in the source will be left alone. And you might wonder, well, why can't we just use and or? You just told me that and or can do these things for us. But in this way, we don't need to remember the details of and or. Now we can just use bit set and bit clear and just remember that a 1 will take the action and a 0 will preserve. So that's easier to remember as programmers. If I want to clear a bit, I'll set the corresponding bit. I'll make the corresponding bit. Set is not a good word. Let's say I want to clear a bit, I will make the corresponding bit a 1, and then that's the bit that will be cleared. All right, and then finally, there's also bit test, which is BIT, bit compare, CMP, and test, TST. These are interesting because they use the ALU status flags, VNZC. So the bit test instruction is actually the same as a logical AND. But the way it works is that if z equals 0, then the bit that was tested is 1, right? We worked through that for the AND case, except the destination will not be overwritten. That's it. So it does not it leaves the destination unchanged. It just updates the status flag. Similarly, the bit compare instruction, CMP, subtracts source from destination, but it leaves destination unchanged, but it updates the status flag. So if we do that subtraction, and if the 0 flag is z equals 1, then the result is 0 and source equals destination. Thus, we've compared the two. The test instruction, TST, subtracts 0 from dest and updates the status flags. So if we do that subtraction and we find z equals 1, then we know test was 0. Also, if we find that n equals 1, then we know that test was negative. All right, thank you. Next time, we're still going to continue with some assembly language, and we're going to look at program flow with jumping and conditional statements. Thanks.